We are now going to provide some definitions about matrices, which is the subject of this chapter. And so we're going to start with an array. An array is a collection of numbers. And so in particular, a matrix is a rectangular collection, and we typically write it with square brackets like this, and then we just list numbers 1, 2, 3, 4, 5, 6. The order of the matrix is its size, and it's given as a row times column order. So in this case, we have 2 rows and 3 columns. So this is a 2 by 3 matrix, and we will refer to the order or the size quite a bit. The entry, also sometimes called the element, is a single number, A, with an ij, and this tells us which row and column to look in. So for instance, if I wanted A13, I go to the first row, third column, which is 3. A square matrix is a matrix where the number of rows equals the number of columns. And these get used a lot, so we'll talk about them in a lot more detail as we go. The main diagonal is defined as any entry where the aij, where I equals j. So in other words, A11, A22, A33 becomes our main diagonal, and it just follows down the diagonal from the top corner to the bottom right corner. A row matrix is a 1 by n matrix, so it has 1 row and as many columns as you need, and a column matrix is an n by 1 matrix, so it has as many rows as you need, but it only has 1 column. An augmented matrix is a way of changing a system of equations into a matrix, and it always looks like some square matrix, most often square, it doesn't always have to be, but it's most often going to be a square matrix, where the coefficients go here, and the equal sign is here, and then this is the constants. And we'll give examples of these as we go. The elementary row operations are the legal operations that can be done on a matrix, and we'll talk about what these are later, but they're very similar to the ones that were our Gaussian elimination operations back when we did 3 variable systems. Now we say that 2 rows are equivalent, or rather 2 matrices are row equivalent if one can be found from another using the elementary row operations. So any matrix that we use the row operations for, the result of that is equivalent to what we started with. A non-zero row is a row that contains at least one non-zero number. So a zero row is then one that contains only zeros, and the leading entry is the first non-zero row, or the first non-zero number in a row if we look from left to right. Row echelon form is when we write this so that each non-zero row has a 1 in front as its leading entry, and anything after that, but everything under that 1 is a 0, and then that repeats per row. So in other words, something like this with a 1, 2, 3, we'll make it an augmented matrix with a 4, 0, 1, 5, 6, 0, 0, 1, 7 is said to be in row echelon form because the leading entry is a 1 and everything below that 1 is a 0. We don't care about to the right, we just care about the below. A reduced row echelon is the same thing where each leading entry is a 1, but all of our other pieces in the non-augmented part are also 0. So it's 0s below and 0s above a 1. So you're only allowed 1, 1 in each row column pair that's a leading entry. So this would be a reduced row echelon form. And it's also possible to do this with a non-square portion, where if I have something like this and a 5, 6, 7, this is still in reduced row echelon form because the leading entry is a 1 and it has zeros above and below it in each place where I have a leading entry of 1, a non-zero leading entry. Gaussian elimination is a process for manipulating a matrix into row echelon form, and it actually works exactly the same as our 3-variable Gaussian elimination that we did before. Gauss-Jordan is different though, where this process for manipulating a matrix, but instead of going into row echelon form, we go into reduced row echelon form. And then the last thing that we're going to talk is a scalar, and a scalar is a single real number, and that's it. It's not part of a matrix. And we'll be seeing scalars later on in this chapter.